Okay, welcome back to the 424 School of Engineering. This is module number 3. Today we will talk about vehicle dynamics. We've covered aerodynamics last time and simulation and modeling. But before I start on the vehicle dynamics, I will talk a little bit about what contributing to pairing means. The reason is I have always people coming to me asking how they can help with designing 424 or the engineering. And I understand because it's obviously very exciting to be part of this. But I've done it for many years now. And the thing that I've learned and what is the situation is 424 is an extremely complicated product to develop, requires a lot of experience. And the reality is the core team will always remain quite small to develop such a project. This is the case for very big open source projects like Linux as well. It's always a small core team of people who are able to really contribute valuable inputs into such a project. But so it's difficult to contribute this way. It's not impossible, but it's difficult. Obviously, what we are making very easy is for everyone to access information, data, and things like today through the School of Engineering. And it's allowed us to find people who were able to contribute over time. And also we will find people that eventually will be employed when the projects are up and running. So it is a way to get people in, but you have to bear with me because it requires also energy and it's a cost to manage new people and maybe train people. And we have done that in the past, but at the moment we're at a stage where on the engineering side, contributing time to 424, we do it mainly with people who are already in the core team. And there is a big focus now on the commercial because we need to find, obviously, the budget to build 424. And I guess this is where also my energy is going to start being diverted to as well, more and more, just to make sure that the project happens. And once we have the budget in place, obviously, it gets easier to organize groups of people and manage people to get involved in the project. And there will be more to do as well. So I just wanted to explain that a little bit. But one important thing is obviously contributing can be done in two ways. Okay, contributing time, I've just talked about it. And yes, we have people that are contributing times, and you see them talking on pairing.com on a daily basis. And these people have got a contract with us and they earn digital credits by investing time. But also anyone can contribute money. And this is an important part of how we're going to grow as well. We can call it crowdfunding, but really it's about allowing anyone to buy a share into pairing the team on the same conditions and the same really buying the same digital shares that I own and all the other contributors own. There is only one level of shareholders, if you like, or investors in pairing. We're all on the same terms here. And I think I'd like to remind everyone that this is a really good way to get invested into the team. And when you invest money, you get digital shares, and the digital shares effectively represent the ownership of the team and the project 424. Now, the way we do it right now is we're using a traditional database on Google Firebase, it's called, and we have we have a ledger or recording of every single contributor's time or money, and we convert everything instantly into digital credits. And we also have a growth of 10% at the moment. So when you have digital shares or credits in pairing, you get 10% more every year. Every day, basically, you get incremental amounts in your wallet. These principles will remain, it will always be at the core of the team that we are. Now, the thing that we need to develop is the system at the moment is on a traditional database, and I'm going to work really hard now to develop this system to a better infrastructure and potentially to put it on the blockchain, which is effectively the best way to trust such distributed team like pairing. So remember that we are on a continuous basis raising money, and at the moment we are raising money to build a simulator, like you can see on the pairing.com page. So there is this page here called Contribute, and you can come back and have a look for yourself. And if I go back to pairing.com here, again, as a reminder, the funding that we are looking for is always detailed here. And at the moment, we are in the process of putting in place a simulator of the dimension of 4 to 4. And we are raising some money for that. And anybody can participate in this. The other thing that we do, we've restarted, is we can contribute to CFD. There is a process here to contribute to CFD, allowing, again, some aerodynamic testing to be done. And that has started again because of the discussions we've had last week following the aerodynamics module, which was really interesting to see that some people wanted to contribute to restart CFD. So we have done that, and there is a 4-step process basically to contribute to that through a credit card payment and get the same digital shares, digital credits, I should say, in pairing.com as a reward. Okay, so the process is fairly simple, but if you have any question, please ask. Let's start the vehicle dynamics module. I'd like to remind everyone that we're on this website called discover.pairing.com. I'm sure you all know about it by now, and all the material that you see is on this website, and all the tools that I am talking about and the data I'm presenting today, you have access by yourself. You have access to all these documents in view-only mode for most of the time, so you can revisit anything that we've discussed today. Okay, so vehicle dynamics. Today I'm gonna talk a lot about balance. I'm gonna say that word a lot, and it's all about getting the right balance. And I'm sure you're all familiar with the understeer and oversteer type of balance. The understeer is when you cannot make the corner because the front of the car slides too much relative to the rear, and you're gonna basically miss the corner and go straight. And the oversteer is the opposite. The rear is too weak, and if you push too hard the car, then the car's gonna start spinning, and you're gonna end up, going this way. So I will talk understeer, oversteer. I will talk balance today. And I will talk, there's been a huge amount of work done to get a very good balance of 4 to 4 around the Nürburgring, not only in the middle of the corner, but from the start of braking, and the braking is very aggressive, to effectively the apex, and then on the exits when you're going back on power. And all this sequence, so we call it, in engineering term, motorsport, we call it braking, entry, late entry, apex, and exits. And all these sequences have to work together and be connected, if you like, in terms of balance. You hear sometimes drivers say the car feels disconnected. In Formula One, some drivers would say today the car felt disconnected. When they say that, what they mean most of the time is they meant that they might have a very variable balance, understeer, oversteer through the corner. In F1, typically you can get quite an oversteer balance on late entry. So when you're trail braking, so you're still on the brakes and trying to make the entry of the corner, the car can be quite loose at the back and will oversteer. But typically in mid-corner, when you're off brakes, off throttle, the understeer builds up quite quickly, and you get a big steering angle put in. So that disconnect between the oversteer and the understeer is a problem. And when you go back on throttle, typically with a very high understeer steer angle, then it's the rear that snaps again, and you get back to oversteer. So you get oversteer, understeer, oversteer, and that window, that big window of balance shift, is described as the car being disconnected. So ideally, you want to reduce that window. You want the car to feel fairly balanced throughout. And by the way, the more understeer you'll get in mid-corner, the more oversteer you'll get on exit, because you put your foot on the throttle with a high steer angle at that point. So you can see where it's all linked from braking mid to exit. So today, we've gone through, as I said, with 424 through the years with our test drivers and our dynamic simulation tools. We've got through a lot of adjustments of the car setup, which I will explain today, to achieve a balance that is honestly very, very nice. It's never ideal. There's still some issues, and I will show you that. And the things we're playing with are typically, so first of all, I'll show you the dynamic simulation in Unity. We've already seen that before, and we'll look at the data together, and you will see where we have balance issues, where things are okay, where things are not. I'll talk about then the parameters we can adjust. So weight distribution. When we talk about that balance and distribution, it's always front relative to the total. Okay, so if I say 50%, it means 50% front, 50% rear. But if I say 40%, it means 40% front, 60% rear. So it's always the front relative to the total. We'll talk about the weight distribution of 424. We'll talk about the tire grip balance, front relative to rear. The aerodynamic balance, and we talked a little bit about it, obviously, in the last module. The power balance. The power balance, it's a four-wheel drive car. So it's how much power we have at the front relative to the total. And that's during braking, because we are regenerating the kinetic energy back into the battery, and under acceleration. And then the roll stiffness distribution, which is how stiff the suspension is at the front relative to the rear. Okay. So these are typically the things that you're adjusting at the track. Not all of them, but typically that's how you keep working on the vehicle dynamics and the car balance. So as a reminder, our dynamic simulation tool is built in Unity. It's a tool called VPP, Vehicle Physics Pro, developed by somebody called Eddie, working really actively in the team. And this software allows us to effectively do dynamic simulation, dynamic testing, and have our driver testing the car. And we've been testing 424 this way for more than 4 years now. And what we've done with it, and that's pretty amazing, is the software runs on my laptop, or can also run on the best simulation, motion simulation platform in the world, called Dynisma, the type of simulator that Formula One teams are using. The same software runs on all sorts of platforms. So if you're interested, you can even install it on your PC, on your laptop. You don't need to drive the car. There is an autopilot mode that will go around the Nürburgring and replicate the best lap that we've done with Damien or Augusto, our test drivers. If you happen to drive and you have a VR headset, and I've tried this week for the first time, it's pretty amazing. You can also drive 424 in virtual reality, and you find yourself inside the cockpit, and the immersion is even better. So that's a fun thing to know. Obviously, here there's a link to GitHub, but that sends you to GitHub and explains to you how to install the simulation. I'm going to now go to the simulation that I have installed on my laptop, and we are going to basically look at the data together and start talking about vehicle dynamics of 424. So for that, I'm going to switch to VPP in Unity. Okay. Again, what you're seeing here is, I'm just checking that I am showing the right thing. Okay, yeah. I'm also checking that the branch in GitHub is the correct one. It's the master branch, yes. The master branch is where we have our latest version of the car and data sets and setup. What you see here is the editor, and it's the way to change all the setup parameters. I give you a few examples here. In Dynamics, that's where you're going to set up the anti-roll bar at the front or the rear. Progressive suspension is the bump rubber, so the suspension is effectively a spring, and then as it reaches the limits, it gets stiffer and stiffer. And also the aerodynamic model, and we talked about that last week. So all the parameters for the car can be found in these menus. Okay, let's run the simulation. Just showing you again. So to put things in context one more time. Let me just zoom out quickly. Okay. So the scenario you're seeing here is the exact scenario that we will do with the real car. Okay, so we're going to park the car here in this little space that exists at the Nordschleife. In fact, this is the same scenario we did with the Neo EP9 when I was working 7 years ago there. We put the car there to start the lap. The reason is it's 1, 2, 3 corners before the start-finish line. And for an electric car, we don't want to do a full lap before we start the real lap because the battery energy is just for one lap. Okay. So I've muted the sound here. I click Q and the autopilot starts. We're just going to watch a little bit this way. I can slow down the time here. I'm going to slow down. You can see the start-finish line very clearly. Okay, when we're doing the lap record, we'll all be on the wall here cheering for the car. Maybe some of you will be with us in this area. That would be fun. Okay, so I go back in real time. Turn 1. We look at the data in a second. Fast sweeping corners and then a few slow corners that are really tricky, actually. The first section is quite difficult on this track. Okay, I'll put the telemetry back. And then let's go back in the car. I'm just going to pause here for a second. Remember that we are using some speed limiter sections for 424. So as you can see, the speed here has just stopped accelerating at a speed of 300 kilometers an hour. The speed you see here is meters per second, 83 meters per second. I like talking meters per second because the car goes from 0 to 100. That's the range of the car, 360 kph, 100 meters per second. The reason we have this speed limiter is because of this big bump in front of you here. And before we put the speed limiter, the car was going too fast over and starting to lose contact with the ground and flying, which was extremely scary. So you see the bump here. And we've applied the speed limiter sections, and now the car accelerates again. This bar here tells you when the DRS is active. You see the rear wing at the back. DRS is just gone off. Automatically, we have a section where the DRS is closed just to give stability in that high-speed corner. And now we exit again. DRS comes on automatically on this car. After half a second on full throttle, DRS opens. As soon as you touch the brake or you release throttle, DRS is closing. So the bar goes on and off quite a lot around the lap. Okay, I'm just going to stop here. We've divided the lap in 5 sectors. The lap is around 5 minutes. So we've done 5 sectors of about 1 minute each. One of the reasons was when we do testing, one full lap of 5 minutes is too long to get accurate time difference, because being consistent is very difficult, but being consistent for 1 minute is easier. So what we do with the sectors is we might drive 3 laps, which takes 15 minutes. We take all of the best sectors and we create this ideal lap. And that's the lap that will be compared to another ideal lap when we have changed the setup. That's a way to get really repeatable testing and more accurate results. Okay, we've just passed sector 1 here. Let's look at some data. So today we're talking vehicle dynamics and car balance. Page 1 of telemetry is quite a standard way of looking at data, and in F1 or Formula E, I'm used to seeing that as page 1. Get always the car speeds, the steering angle, and then at the bottom we put throttle and brakes. Okay, and typically the brake pressure is always of that sort of shape. Very hard braking, obviously at high speeds, when downforce is on the car. And as the speed decreases, we have to release the brakes because there's less loading and we're starting to enter the corner as the steer angle increases. Okay, that doesn't tell you much, but this is page 1. If we start to, so for me, the big rule of looking at, obviously the driver will tell you when he has issues, but I love looking at the wheel speeds, individual wheel speeds. So let's have a look. It's on page 3. These are 4 individual wheel speeds. And that's when you start noticing potential problems. So I tend to always say 4 wheel speeds tell you 90% of the story. So let's have a look. This is turn 1. The braking point is 240 kph, and the apex speed is 76 kph. It's quite a bumpy braking zone, turn 1. You can see it on there's a big bump here. You can see how the wheel speed's deep. So at this point, this is, we're looking at the rears. You can see how the rear wheel speeds have dipped. The light blue, I'm going to zoom here. 135 kph, 133 for the rears, where the car is at 180. So the rear wheels are going 45 kph slower than the car. It's a fair amount of slip. The driver would call it a lock. He would say, I've locked the rear wheels. And the way it feels it in the car is the car suddenly steps. And if it gets worse, it would spin. Obviously, for the car to spin, the rears would have to really, really slide more. The reason they don't lock and stayed locked is because it's a bump. The car has basically gone in the air and come back. So that's very typical of high-speed hard braking. The weight transfer to the front, the rear is fairly light, and any bump makes the rear sort of wants to stop. So you can see one bump and a bigger one here. And towards the end of braking, it's mainly the front that you start locking. This is a big lock at the front, actually. Front left is gone to 0. And in slow speed corners, you see that quite a lot. You see that in F1, you can see the wheel stops. So these things tend to happen quite often. I would say you can still do a very fast qualifying lap even with a single wheel, front wheel lock, if you're able to bring it back fairly quickly before the apex. But the driver will still complain about it because he will feel like he had to release the brakes a bit in order to control that front wheel. He can see it. It's harder in a car with bodywork on top, but he will feel it in the steering wheel. And the way he will feel it, and if you drive the simulation, you do feel it, is the steering load is getting a bit lighter because one front tire has lost the grip. So you feel it in the steering. So that's a problem. But this is typical of turn 1 because of the amount of bumps as well. The other corners are not as bad. If you look at the exits, so on exit, what we're looking at is obviously the wheels are going faster than the car at that point. You see the car speed is still green. Here we are looking at positive slip. And We want to know, it's a four-wheel drive car. We want to see, is it the front or the rear that slides the most? In fact, if you look here, first of all, the left and right goes at exactly the same speeds at the front and at the rear. You can see 1.9 left and right, and the rear is very close as well. That's because as soon as we touch the throttle, the mechanical diff is locking the diff. This is the most stable way to exit a corner. You lock the diff front and rear. And all you do then is control the amount of power going front to rear in order to avoid spinning the front tires or the rears. So here we are in a pretty good scenario, actually. They're sliding more or less at the same amount. Okay, so I'm fairly happy with that. Okay, let's keep going. Let's go to turn 3. The braking is fairly good here. There's no big amount of lock, just a little bit of front locking, but it's not much. Here you get a little bit of higher front slip than rear on exits. So it might tell you that if anything, we've got our power balance is slightly too much to the front at that point. So you can see so many different aspects of the car balance. The other thing I like to look is how the diff opens and closes. And you can see the diff is fairly open on entry. The reason I'm saying that is I come back to turn 1. When you see the front tire locking, the other side didn't lock at all. So the diff is completely open and allow just one tire to lock. On exit, as I said, the diff is always very locked because we use the motor torque to lock the diff. So we never have just a single wheel speed going up or down. It may happen, but it's rare. The reason we have to open the diff in this area is if you don't open the diff, the car doesn't want to turn and doesn't want to make it to the corner. But then we could argue that you could lock the diff a little bit more to remove or reduce the front locking on that inside wheel. Yes, you could, but it would increase the understeer because you would, but by linking with the diff the two front wheels, you're creating basically a moment around the car that wants to understeer the car and miss the apex. So the driver will not like that. So we really want the diff to open. Okay, so we could keep going like this, but I think we've seen what I wanted to show you. Okay, again, this corner is quite a long braking zone. I'm fairly happy with the brake balance because if you look at the first part of braking, nothing much happens. It's a hard braking. I go back to page 1. It's full maximum braking force, in fact, on the pedal. Oops. And the wheel speeds, there's a little bit more sliding at the front than the rear, but there's more loading as well. But the wheel speeds are really following. And towards the end, the inside front will start locking, but it's not a huge amount. So I'm fairly happy with that. And look on exits, it's not like the front is oversliding more than the rear. So you can see if you look at this, that's a fairly healthy picture, and we're pushing really hard here. And I want to say this is the result of months of development to achieve this. We used to have much bigger locks. The rear might lock first. On exit, we used to have a lot of front slip. We had too much power at the front relative to the rear. I'll show you what we've done on the power distribution in a moment. I like to use this corner on the track. You can see on the map, it's this corner here. And it's that long, it's just a very, typical V-shaped corner, and it's fairly flat. There's not much camber on the track. So it's a nice corner to look at the balance of your car, and there's no bumps. Okay. The other thing I can show you quickly on the using the telemetry, I talked about the differential, and I want to talk to you a bit more about it here. Let's go back to that long corner that I like. And I want to show you, it's a bit difficult to see here. Excuse me. But there's an interesting channel here, which is, so this is the differential in the transmission front and rear. And it's extremely important to the balance of the car. I talked to you how the diff was opening towards the late entry and very closed. You can see it here on this channel. This is the speed differential across the left and the right wheels. If you look at the, I'm going to hide the rear. This is the front. When it's 0, it means the diff is locked. There is no speed differential left to right. You can see up to this point, up to the middle of the braking, the diff is fully locked. And the reason, again, is because we have a mechanical diff that locks proportionally with the torque we apply on the diff. And the torque is coming from the regenerative braking, and that torque is going to the ramp system and is locking the diff. As you release the brakes and the regen goes off, the diff starts to open, and now you allow one wheel to move relative to another. But when you go on throttle, the ramp is quite aggressive, and we are locking the diff straight away. At the rear, we also open the diff, but it's a scenario where the wheels want to stay together because we are not braking very extremely hard on one, we're using one wheel. So even if the diff opens, we only have 2.5 kph wheel speed differential. It's what we call the bicycle effect, or the fact that one wheel, the outside, has to travel more distance than the inside tire wheel. So the outside is going to rotate a bit faster, okay, by about 2.5 kilometers an hour. But at the front, there's 29 kph difference because we are locking one. Okay, so this is the diff. The other channels are telling you the torque that effectively goes across the diff. So I talked about the speed difference left to right. This is the torque difference left to right. As you enter the corner, there is a bigger and bigger torque difference because you're starting to steer, and one tire is more loaded than the other one. So one wheel is having more reaction torque through the drive shaft than the other one. And you can see it's building up to the point where, so the yellow trace here, up to the point where the friction in the diff is opening, and we cannot transmit that torque across the diff anymore. And you see that it's basically meeting that curve, the blue one. That blue curve is how much torque could be maximum transmitted across the diff. So the yellow one is the actual torque. The blue one is how much maximum you could transmit when they meet. Basically, you're starting basically to slide. The diff starts to slide. It's like a clutch. And at that point, the diff, the torque across the diff reduces back to 0, and the speed across the diff is different, left to right. So we've modeled the diff in very accurately because it's something I wanted, and I asked Eddie to make sure we have something really accurate here because it affects the car balance quite a lot. When I was looking at this plot, it just reminded me, I only realized the reason why we did some tests recently with a reduced amount of regen because we had a battery option to look at. And I adjusted the brake balance, so it should have been the same. But Damien complained that the car was different on their braking. I just realized I had forgotten that obviously what I had changed as well is the amount of locking in the diff, because the regen being lower means there is less connection in the diff, and the diff will open faster. So it's something I'll have to look back again. So that's interesting. That I just remembered as we were looking at this. And then let's keep going a bit. I want to show you. There's so much we could talk about, but just to actually, let's look at the slip angle. I talked about understeer, oversteer. The way we define understeer as an engineering metric is we look at the difference between the amount of slip angle of the front tires versus the rear tire. So here you see front and rear, you see the 4 tires slip angle. As you all know, slip angle is the relative angle of the tire with the velocity of the track, and that's what builds your lateral force. So in the middle of the corner, you're sliding at the maximum slip angle. In fact, if I look at the mid corner here, the front tires are sliding at 8 degrees. The rear tires, 2.6, 2.7. So there's a fair amount of understeer in the car at this stage. The understeer being the difference between front and rear. If we do the difference, we look at understeer angle at the back, at the bottom here. We have about 6 degrees of understeer. It's a little bit too much. I would like to have less. You always have some understeer in the car because it would be nearly impossible to drive a car that always oversteers. But I think we have a bit too much understeer in 424, and it's something we've been working on, and we still have more work to do. And it's one aspect is I think it's a feature of the simulation as well, that in a simulator, driver tends to put more steer angle because we are not modeling the temperature on the tire and the thermal effects, so you cannot overheat the tire, and it gives you sometimes a bit more grip. So I have to remind our driver to not put too much steer angle. Okay, so that's the understeer channel. And on the powertrain, again, a bit difficult to see here with the colors, but you've got channels that are telling you what power balance we have. And all I want you to see here is between braking points, so the power balance are these channels here in the middle. Between the start of braking to the mid corner to the exits, the amount of power we send or we regen at the front relative to the total keeps changing all the time. Under very hard braking, we're 70% at the front. Why? Because we are braking hard, we have a lot of potential at the front, so we are doing our regen 70% at the front and only 30% at the rear. We had this -4% that you saw, the second channel -4%, called the offset. This is there's an active system on the car where when we detect that the front or the rear is locking, for example, relative to the other axle, then automatically we will adjust the power balance to try and reduce the amount of locking. And it's a bit like, and we do it on exit as well. So it's a bit like a traction control anti-lock system. It works relatively well, but it will not prevent the big events of locking. It's just a little help. As we release the brakes and we turn, the power balance goes to the rear. You can see now we're at 15%. The feed forward, which is what we calculate, is 15%, which means, and mid corner, you still have some torque. You're off throttle, but we have like what we call the overrun, which is like engine braking. It's a negative torque that slows the car a little bit like a handbrake. Why a handbrake effect? Because I just said the balance is 15%. So all of that torque, or 85%, is at the rear. So it's a little bit like pulling the handbrake gently, just to let the car rotate a little bit. It's a nice little effect that helps the car rotate. And as soon as we touch the throttle, the balance goes back to the front. So we were at 15%, and now we're going back at full throttle. We're going at 33%. Why? Because we have one motor at the front, two at the back. When we're at full power, full delivery, we basically use the motor capacity And at that point, we have a third of power at the front, two-thirds at the rear. But in the part throttle phase, when the driver tries to feed in the throttle, we are playing with that power balance just to make sure the car, if we send too much to the front, we'll start spinning the front and the car will understeer, and the driver will have to go off throttle again, otherwise he will go on the curbs. If we send too much to the rear, the rear will start sliding a bit. So it's a very, you do 5% changes here and there, and it really affects the balance and how the car rotates. It's a very nice way to tune the car balance. And up to this point, I haven't discussed even suspension. And I think a lot of you might think vehicle dynamics suspension. We're going to, especially with 4x4, and in F1 as well, but with 4x4, it's an aerodynamic car. The loads are dictated mainly by aerodynamics and by the powertrain, and it's a four-wheel drive car. And we have this ability to shift the power balance front to rear, just using numbers and software. So it's extremely powerful to play with the power balance instead of playing with dampers and suspension, even though we are. But the best way to change the balance of the car is playing with just changing some numbers in the software, sending different amounts of power front and rear. And then the last thing is the aerodynamic balance, which we talked about last week. But I will stop. I will stop sharing now this VPP window. I welcome any question on this before we move on to the next section. Anybody's got any question on this telemetry analysis I've just done? So if you have, you can raise your hand. Yes, please. Vosej.
Wojtek, it's
Wojtek.
Wojtek. I had a question about the chart out with speeds of wheels. The chart is actually scaled in kilometers per hour, but you talk about the rotation. I'd like to understand what actually this number mean. Is it the rotation, linear velocity of each of the wheel?
Okay. So here, effectively, everything's in kilometers an hour. What we've done is what we measure on the car is the rotational speeds.
Mm-hmm.
In RPM, for example, rotation per minute. And then we are just using the radius of the tire just to get a velocity. But you're right, the actual measurement is the rotational speeds. But we always do that in race car. We use it can be a constant number or it can be a variable number with different parameters. It's what we call the rolling radius of the tire. How do you go from rotational speed to? It's basically the tangential speed of the contact patch.
So it is just scaled rotational speed without taking slip into account.
It's exactly. That's exactly right. So it's not the velocity of the track at that point, it's the velocity of the circumference of the tire.
Okay, that's
So imagine if you lock your tire, that speed becomes 0 because there is no velocity, the compound doesn't move anymore.
Okay, and you talk also about locking the diff. How physically the diff will be locked?
The diff is like a clutch. So it's got plates. So like a clutch, it can be 6 or 12. You've got there is drive shaft coming from the left and the right. Each wheel has got a drive shaft, and what connects the two drive shafts is there is a clutch between these two drive shafts inside the diff, and then there is the bigger outside wheel with the gear that will connect to the motor. So the diff has got torque coming from the outside from the motor, and when the big gear of the diff has torque applied to it, and then you've got a system of ramps that are basically just mechanical parts that that are sliding against each other. But what it does is when the torque is applied from the motor, it pushes on the clutch. It closes the clutch. It's applying pressure on the clutch.
So it's a passive system, right?
It's a completely passive system.
Okay, I see now.
It's called a limited slip differential. And the reason we are not using active, we could use active diff, but this would require a hydraulic system. It would be heavier. And believe me, what we can do with a passive clutch is very, very good.
Mm-hmm.
It's what we use in Formula E, it's what we use at Le Mans, and it allows you to do more or less what you want to do, and it's extremely light. It's a lightweight solution.
Mm-hmm. Okay, thank you. And teeny remark, when you are showing these charts on transparent background, at least on my screen, are not very clearly visible.
It's
so
difficult. Yeah, I appreciate that. Yeah. In fact, we might put a black background. Sometimes when I have to move the car, which I'm doing now, but I agree with you. It's to a dark area with trees behind. It's not the best way to. Or maybe if I do this, a bit easier to see here.
much better here.
Can you see a bit better?
Yeah.
Okay. But I think we're going to change that and put a darker background. Yes. Okay.
Mm-hmm.
Thank you for your question. Anybody else has got a question? Martin? I can't hear you, Martin. Sorry. Your sounds very low. We can hear you, but your volume is very, very low.
Is it better here?
A little bit better. You can try again. Or put your... you can put a question in the in the chat as well. Okay. Well, while Martin maybe writes his question in the chat, I'm looking at the chat today. Actually, I missed the question last time. So there's a question from Shirshak, and he says, "How is your car taking racing line? Is it some XY coordinate you have given before?" So your question is related to Autopilot. Thank you for asking this. Because what I'm showing here, I'm not driving the car. All I'm doing is pressing Autopilot. Yeah, so what we're doing here, I love this system, it's great. We've recorded all the driver inputs, throttle brake, steering angle, and also the exact trajectory the car went on. And we in X, Y, and Z. And when we play Autopilot, we are launching the simulation dynamically. We are applying the same inputs, throttle, brake, steer. And if you only do that, the car will follow, but after a while, it will not follow the same trajectory. So now we are looking at the trajectory we had recorded with Damien or Augusto, and the current trajectory, and the difference is called the error. And we're putting a PID, we are putting a controller force. In fact, there is here you go. There's a page for it called Autopilot. The error in white is the distance between the current trajectory and lateral distance to where we want to be. We want to put the car back to where it was. So we're applying a force with a PID system, and this force is in Newton here, and it keeps the car always maximum 1 millimeter from the trajectory. But look, we're going to play a little game here. I'm going to stop Autopilot. I've stopped Autopilot. The car stops because the brakes comes on. And I can reapply Autopilot. And the car now, I'm going to pause here. You see when I reapplied Autopilot, it said we are 4.5 meters away from the trajectory. You see this white? and it starts applying a force of 13 kilonewton at the front axle to push the car towards the trajectory. And what you will see is with time, the error is going to go to 0. I'm going to carry on playing. Oh, now it's snapped. You can see there was a small oscillation, and now we are on the trajectory, never more than 2 millimeters away. But for that, it had to apply, some fairly big forces. So isn't it a cool system? It works so well. We can stop the car again, and then start again with Q. Boom. We are 3 meters away. It's pushing the car. And look, we are half a meter away, and now bang, 0. And now it stays on. I like to show that because it's something we've developed hard in the first year, just to have something we can test with. Yeah.
Yeah. Hi, Nico. Sirshak here. So
Hi.
yeah. So basically, so you have a PID control and you have a desired trajectory, and your PID control is making sure that your actual trajectory is equal to the desired trajectory, right?
We are looking at the error in the lateral distance between where we are and where we want to be.
Yeah.
And we have a PID system. It's a PID controller.
Yeah.
And what we do is we apply a lateral force, and that's how we do it. So the car drives normally, but we are pushing it with, I call it hand of God. It's like a force from the outside. It's a bit like a Scalextric.
Yeah.
There's like a finger that follows the trajectory. We don't want to disturb the car too much because we want a true dynamic simulation, but we are doing it just enough so the car stays where we want.
One more question. So let's say you have the desired trajectory, then how is your car? Let's say, so if you have a trajectory, then you must have a velocity profiling for that exact trajectory.
Now the velocity is free. It's purely a result of the driver inputs.
Okay.
The testing we do is with human drivers. We are not. I like to remind you that we are not using Autopilot to automatically drive the car around the track. We cannot do that. We've tried. It's too complicated.
Yeah.
We need a human to drive first. Once the human driven, we have throttle, brakes, steering angle that work for that car and that setup and the trajectory, and then we can apply Autopilot. The good thing with Autopilot is you can then change some setup and see some differences and effects. I use it a lot when I ask my driver to drive. I don't do it myself. But when we get the good driving data, then I can apply some small changes to the diff, to the power distribution, and I can see the effects on the wheel speeds and things like that.
Okay. All right. Thank you so much.
You're welcome. Okay, Martin, I've got your question. So at the rear, the car has the motor connected to the diff, or one car per wheel. It's the two motors are connected together as one motor, and then they go to the diff. We are not doing motor wheel. We are not doing one motor per wheel. It's too heavy. You will hear me saying that for years, guys. Some systems that I know people are talking about, they are too heavy for us. Having one motor per wheel. One problem with that, of course, it allows to do left to right torque vectoring, but we don't really need it with 4x4 because we do front to rear, and that's powerful enough. The problem with one motor per wheel is when you're limiting your torque, because suddenly your maximum torque becomes limited. Instead of being able to transfer some of the two motor torque to the one wheel on one side, now one motor has to always drive the same wheel. It cannot apply some of its torque to the other wheel through the diff. So you're actually becoming limited by the torque. You're reducing the performance of the car. And it's also a double transmission system. It's heavier. It's like having two gearboxes. So I hope that answers your question. Okay, and I've got another question from Yash. When I explained about understeer, oversteer, with respect to the difference between the slip angles of the front and rear? Does that also account for the understeer oversteer induced due to the power difference? Yes, it does. Exactly. So the understeer that you see from the slip angle at the end is more or less the result of everything. Okay, so if you start playing with aerodynamic balance, power distribution, and the car snaps and oversteers, you will slip on the slip angle. Okay, let's move on. Thanks for your questions, really good. I want to go back to our presentation here. I need to also stop the simulation for a minute. Okay. Okay, good. So really good. We've looked at a lot of data from Unity. I want to break it down now to various aspects. One major parameter for balance of a car is weight distribution. Weight distribution is front to rear weight. On 424 now, we found that the optimum weight distribution is 47%, which is about it. The center of gravity is roughly about there. You can see the battery, the seats. So we have a bit more weight on the rear than the front. So 47 front, 53 rear. That number is extremely powerful, but it's also a number you cannot really change at the track, or it's hard, especially on the car with like 424, where we don't have ballast, so we don't have weight that we can move around. The car is as light as it can be. It comes down to making sure that in the design process, we understand what weight distribution we want, and then we design the car. We move things in design, especially things like the battery, because it's quite heavy. So if you open this spreadsheet here, this is a bill of material. It's a list of all the parts that make up the car. The first page here is not all the parts because it's got 83 entries. So it's more like what we call sub-assemblies. But actually, if you go in the master page, in this master page, you've got 3,000 entries. This is part by part. But this was done for the old LMP1 car, and we still use some of that. But I want to go back to this page here because it's a bit easier to work with sub-assemblies because we are managing 83 entries here. The car is divided by the chassis, powertrain, rear casing, and then front left corner. So we've got 4 corners, the floor, and then some bodywork, the nose and the splitter, so the front wing, we could call it, the rear wing, okay? It's a really powerful spreadsheet because what it gives you is the actual center of gravity location. Not only that, it gives you the inertia tensor as well. So the inertia tensor is effectively the inertia in the rotational mode. So this number is when the car wants to rotate in roll. This is the yaw inertia, and this is, sorry, Y. It's the pitch inertia, and this is the yaw inertia in Z. Now, the calculated weight distribution for this spreadsheet is 47.9. And I said we want 47%. In Unity, we can move it very easily. We just change a number. And we've done lots of testing with our drivers, and we found that 47 for us was the best. Initially, we had 48.5. So imagine we had more weight at the front. The front tires were more loaded. And when we did that, we had a bit too much understeer because in high-speed corner, there's so much load at the front that you're saturating your tires and you start to understeer. It's also giving you understeer on entry in slow-speed corners. Now, if you move the weight at the back, which we did, you start to get a bit more neutral or oversteer balance, and the car starts to rotate a bit better on an entry on slow-speed corners. If you go too far rearwards, you start to oversteer, and the rear is just saturated. So we found for us, but we didn't only move the weight distribution. When we did this test, you have to readjust aerodynamic balance and various numbers. But we found that for us, 47% is the ideal number. The car at the moment in design is at 47.9. So we still have to move a few things to the back to achieve 47. And it's something that takes time because it's a decision in design, but we're going to get there because the battery just needs to move by, I think, about 50 millimeters to the back. Okay, so for every entry, you've got a mass. The chassis is just a carbon chassis with nothing, 85 kilos. And then you've got an XYZ coordinate of the center of mass for that subassembly. You've got a driver, for example, 75 kilos, again, is located here. And you can move any of these numbers. Let's look at the battery, 280 kilos. If I move the battery by 50 millimeters back, so it will go to 1875 in X. Okay, the weight distribution is now 47.5. It was 47.9. So we need to move the battery by about 100 millimeters if we want to achieve what we want. The reason why I haven't done it yet is there are other things that are moving. The rear tires are getting a bit bigger, so they will be a bit heavier. There are some updates to do before I move the battery itself. But you can see how precise we have to be in design as well to achieve that weight distribution. Okay? Any question on this before I move on to the next section? Okay, so we've got one question in the it's David. Hi, David. In the chat. So I wonder whether the driver you choose would have a preference for over understeering. Yeah. So yes and no. When you come to that level of performance, what you find is the setups that driver will choose is extremely close. And some drivers, and I know in F1 maybe Max Verstappen likes or can drive a car a bit more oversteery. If you can drive a car that a bit more oversteery, you tend to go a bit faster. Why? Because you're not saturating the front as much, and you can use a bit more of the rear potential of the tire. Remember, the slip angle was high at the front, not so high at the rear. There is a bit of margin left at the rear that we are not using. So we need to increase the oversteer. Some drivers are struggling to drive like this. So yes, there are some differences. So that is the answer. Okay, we have another question from
Wojtek.
Wojtek. Yeah.
When you're calculating tensor of inertia, basing on this sheet, do you treat all these entries as lumped masses or more distributed ones?
Yeah, they are actually single point mass.
Mm-hmm.
And it's working because we've broken the car down in 93 entries. In reality, you're right. The chassis itself, for example, 85 kilos, has got its own tensor of inertia that should add actually. So that overall tensor of inertia tensor should be slightly higher because there is also the individual parts that have got some rotational inertia. But believe me, it's extremely small effects. The biggest effect is the distribution of the center of gravity of these 83 parts.
Mm-hmm.
So this is a fairly good way to do it. And I say that because on other projects, I had the opportunity to look at doing it in a more complicated way.
Mm-hmm. Also for the driver, it may be more useful to treat it as a full rigid body than a mass point.
Well, it's the same for all of them because the driver is the same as, he's moving a bit, but everything's more or less a rigid body. What I mean is, at the moment, I treat them as a single point mass instead of a bigger a bit in there, with some rotational inertia associated with it.
And by the way, when in your dynamic model, do you also take into account the gyroscopic effects of rotating elements inside the car?
Yes. So gyroscopic effect will come from these out of. You see in the inertia tensor, we have it's a 3x3 matrix. The numbers on the main axis are the pure pitch, roll, yaw rotations, and out of the main axis there are the gyroscopic effects. So we do have that in Unity. Yes.
I mean rotating parts inside the car, like shaft, for example.
Okay, sorry. Yeah, absolutely. So these numbers are not in this; they're in the Unity. Effectively, the wheels have got rotational inertia. Yes, because when you accelerate and slow down, the wheel has got its own rotational inertia.
Well, this is obvious because you have to transfer the force to the steering wheel, for example. But other parts like shaft or diff.
Yeah, the biggest parts. So it's along the transmission. The biggest effects are from the tire and the wheel, because that's a fairly big mass to rotate. But the other one is the electric motor. Even though it's quite small, it's going through a gear ratio of about 8:1. So its rotational inertia is multiplied twice by 8. So it's 8 times 8, 64 times the inertia of the motor. That's what is seen by the wheel. So what you find is, if you had to take the wheel in your hand and try and rotate it, the resistance you would feel is coming half from the tire and the wheel, and the other half is coming from the electric motor. It's got very high rotational inertia. And that's all modeled in Unity. Yeah.
And as for the balance of the weight distribution in the future version with hydrogen, do you plan to keep to have some mechanism to keep this 47% as the hydrogen goes off?
Yeah, but the hydrogen car is going to be a redesign, and there will be the numbers are going to move, things are going to change. It's not sure that it will be 4-wheel drive. In fact, Le Mans is writing the rules right now. There is one side that wants a 2-wheel drive car, one side that wants a 4-wheel drive car. If you go to a 2-wheel drive car like F1, it changes a lot of parameters.
Sure.
Because suddenly you cannot have that power at the front, and obviously, especially on exits, but also on entry, you cannot play with the diff at the front. So the weight distribution changes a bit. It tends to be slightly more to the back. So we're 47 and 4-4. If you do an F1 car, for example, with all the power at the back, your weight distribution will be more like 44%.
But I ask more about not this exact number, but rather the conditions with changing the mass during the race.
I don't understand that, sorry. Oh, with the fact that the fuel load is going down?
Yeah.
Okay. Well, typically the fuel cell or the fuel load, or the hydrogen is situated very, very close to the center of mass. So it doesn't have a big effect on weight distribution. A little bit, but not much.
Okay, thank you.
Okay, good. Okay, let's move on to the next section. Good questions. Thanks, everyone. So the next one is the tire grip balance. Okay, so we talked about tire model in the first module, and I explained how we model the tire in Unity and all of that. I just want to reopen that quickly for you, and also say that in the grip model tab here, say that the same that we have with weight and aerodynamics and suspension, we also have a split of potential on the tires. They are not the same tires front and rear, and there's a good reason for that. So you can see it here. So we have a table of grip. This is the lateral grip. This is the longitudinal grip. And then you've got the front and the rear. And what you find is the front tire is weaker. It doesn't produce as much grip as the rear. And you can see it on the plot here. There's one line for the front, one for so the rear is the top one and the front is the lower one. The same for longitudinal. And the split is about 6%. That split is fairly small on 4x4, again, because it's a four-wheel drive car. We've tried to look at, so the rear tire is more or less as good as it can get. We will not get a tire that's got more grip than that. But the front tire, we've got a choice. We can put we could put the same tire as the rear. We've tried and it doesn't work. We could also put a smaller tire and drop the grip at the front. So what we found with 4x4 is we want less grip at the front, but not too much. Just 6% difference is really good. Again, the reason is because we are four-wheel drive car and we have quite a lot of power to use at the front on exit. So it's the way we found the best balance for us. Interestingly, it will affect aerodynamics as well. If you look at Formula One cars, their front tires are fairly smaller than the rear in width. I would expect the split would be bigger. They probably have 10 or 15% less grip at the front than the rear. But that's also because all the power is at the back, the weight distribution is more at the back, everything's more at the back in the F1 car. So with 4x4, everything's a bit more in the middle. Yeah, just something I want you to get a feel for. And believe me, I really love working on a car like 4x4, having a car that's a bit more together, and it makes the balance window together. I talked at the beginning of saying F1 cars tend to oversteer a lot on their braking, then they understeer, then they oversteer. With a four-wheel drive car, you reduce that window, and the car is more connected. Okay, so that was for the tire grip balance. I'll move on to the next one. Aerodynamic balance, again, a very important number, of course. And we looked at this before, but I want to revisit quickly and talk about the balance specifically. I explained in the aerodynamics module how we use CFD to create these maps. And if we look at the table of aerodynamic balance, this is front ride height from 10 to 70, and then we have the takeoff high ride heights. And then the rear 20 to 100. Typically, we spend a lot of time in the middle at 40, 60. Remember, I did show you this plot before. These are all the points of ride heights combination we are using around the track. And we're spending a lot of time, actually mainly in this region here. And the 40, 60 is the yellow point. Okay. So at that point, the aerodynamic balance is 44.5. Note that it's a bit lower than the weight distribution. We said weight distribution is 47, aerodynamic balance 44.5. And that's typical on a high performance race car. I always find that you need aerodynamic balance just under weight distribution. And the reason for that is as the car gains speed, obviously in slow speed corner, what dominates the balance is your weight distribution. There's less aerodynamic load, so the vertical loads on the tire is more dictated by the static load, so the weight distribution of the car. And at that point, you have a bit more weight at the front. What you do when you build up speed is you are adding more more vertical load at the rear than you do at the front because the balance is 44.5. So as you build up speed, you're loading the rear more than you load the front. That is giving you stability. It's building a little bit of understeer in the car. And this is required because it's easier to control oversteer in slow speed, but not so much in high speed. So you see how we use aerodynamic balance to give a bit of stability in high speeds. You never would put aerodynamic balance in front of weight distribution or higher. Having said that, you see that some points on the map are going to 50% when the car is extremely low. And actually, this is when the car is at the highest speeds as well. So that's a problem. because we don't want to increase the vertical load on the front. That will actually induce some oversteer in high speed. So one thing we do with 424 is, I explained before that the flap is elastic. We have a spring, we've got parameters here, and the flap is dropping with car speeds. And by the flap dropping, we are reducing the aero balance. Instead of being 50%, it's staying around 44, 45. In fact, I will demonstrate this quickly in Unity, so let's go back there. Okay. Let's go and drive. Here we go. Gonna do a bit of driving, gonna accelerate a bit, and then I'll stop. Yeah. Okay. Hopefully the telemetry is clear enough for you guys. So I want to have a look through this sequence here. If I look at aerodynamics, okay. So we come out of a slow speed corner and we go to a high speed section. And at this point, the speed of the car is 326. So we've gone from low to high speed. And what you're seeing is the flap. So I'm gonna keep the DRS here. I'm gonna hide this. Okay. So it's harder to see here because we have DRS coming in. Obviously, I wanted to show you how the flap drops. I'm gonna do it in a different way. Let's keep driving a bit somewhere else. Here's a section where you can see it clearly. Okay, let's look at our favorite corner here. So DRS is closed all the way through the corner. So you can see how the flap angle is -2 degrees here. And in the mid corner is 3 degrees. You see the red going up? So that's the spring. At very high speed, the DRS was closed at that point. So DRS doesn't impact anything anymore. The flap is -2 degrees. And as the car slows down, it goes up to 3 degrees. And as you accelerate again, with speed coming up, it drops again. Then we open DRS and it drops a lot. So you see how we make the flap moving. And the reason we do that, as I said, is that now we look at the balance, the aerodynamic balance. You see this trace here. Because the car is moving up and down with ride heights, you see the ride heights on the cursor. We are 20, 33, but in mid-corner, the cars goes to 50, 70. And as I just explained, if we wouldn't move the flap, the aerodynamic balance will go from being very much to the front, and in mid-corner, it would go to the rear. So by moving the flap, we're reducing these effects. So here, I look at the aerodynamic balance. We're at 46, and in mid-corner, we're 43%, 42. So we only have a 3% change in aerodynamic balance instead of 6 or 7% if we don't move the flap. So you see how we use the flap, but we can also change that spring and make that effect a bit bigger or smaller. And we will have to wait for driving the car in real life and getting feedback of the driver might say, balance in slow speed is very good, but in high speed, I've got a lot of understeer. That would mean maybe that the spring is too soft and the flap drops too much. So we'll stiffen the spring. Or they'll say the opposite and we'll soften the spring. Okay? And just to finish on that, there's a view here. Well, let's look at, let's have a bit of fun. Let's see if we can see the flap moving live. Okay. If I, okay, we're in DRS, so the flap is low. Up, you see the flap goes back up. And now it's at slow speed maximum. You see how high the flap is? And now we're going to accelerate, and the flap's going to go lower. Now we've opened DRS, so it's dropped a lot. Wait for when DRS is closing again. Up. And now you see how the flap now is on the spring. It's the higher movement. The big movement is the DRS. And the DRS is linked with the you can see the rear wing opening and closing. Okay, so you see how the front flap has got both a spring effect and a DRS effect. All right, any question on this? I've heard something, so.
Yeah, hi Nico, Sushak here.
Yes, please.
Would you like to show me the tire data again from in the Google Sheet?
Sure. Bear with me.
Yeah, no problem.
Okay.
Yeah. Yeah. So I can see the vertical stiffness. It says 450 Newton per millimeter, right? So vertical stiffness also changes with tire pressure. So is this data taken at a particular tire pressure?
Yeah, absolutely. It's taken at the pressure that, in this case, Michelin would want us to run. So we've just defined that we will run at that sort of pressure, which is more than 2 bar in this case because of the velocity of the car is very high, and we've come up with that vertical stiffness. What you find is the pressure anyway. We change the pressure on race cars by not very much. It will go down to maybe 1.8 bar, 1.7.
Yeah.
And the vertical stiffness will change a little bit, but not too much.
Okay.
Some of it comes from the carcass as well. Okay.
Yeah. Thank you so much.
Yeah, you're welcome. Any other question on this? Or the flap aerodynamics or anything? Okay, MS?
Yeah, hi Nico. Can you hear me clearly?
Yes.
Hello. I'm a little bit to the session. That's why, sorry if you answered this question before. So I have a general vehicle dynamics question. You know, in racing, one of the most important component is the tire, because in racing, we want to drive at the maximum performance, which is limited by the tire itself. So my first question is, which parameter are you most considering while the tire selection, and how are you choose your optimum tire in terms of vehicle performance? And my second question is, do you have any tire model? Actually, you have definitely a tire model, but are you modeling your tire mathematically by yourself, or are you providing this tire data from a certain tire company?
Yeah, the tire model, I'll start with the end, but the tire model is, if you watch our first module, it's on YouTube. I talk about the tire model. It's built by us. And in VPP, in Unity, we've done our own way of describing the slip angle, slip ratio curves. It works like Paseshka, but it's a bit easier to parameterize. And we wanted to do it this way. The selection of tire, so the way we find a tire for this type of car, for 4x4, typically will be, first of all, what are the vertical loads on the tire? This is a car that's going at extremely high speeds. It's got lots of downforce because of the nature of the track. And typically the tire manufacturer, the first thing they will want to know is what will be the maximum load that the tire will have to take, and the maximum speed as well. That will define the sort of carcass that they will have to use, just purely from a reliability point of view. Okay, we don't want the tire to explode. That's the first thing. Once we know that, and in our case as well, from a cost point of view, I've asked that if we could use existing molds, because they will do a specific tire for us. because it's a different type of car and we want maximum performance. But the mold in which they build the tire is an extremely expensive kit. So we want them to use an existing mold, and they have various dimensions they can do. So that's one other thing. And after that, once we've discussed these bigger parameters, and the tire pressure is dictated as well by the vertical load, just to make sure the carcass will not degrade. Once we've discussed that, then it's the compound that matters, and the compound what gives you the grip, obviously in combination with that carcass and how strong the tire is. And typically the compound will depend on the track temperature you're going to be on. Is it a compound that needs to work at high track temperature or low track temperature? So I've explained that for 424, typically we know that we will go on a fairly cold track because it's an electric vehicle. We want fairly cold ambient temperatures to cool the battery. So it will be typically a day. Ideally for us, it will be a day where track temperature is, 20, 25, 30 degrees, no more than that, with not too much sun on it. So this way they they know which compound they can use, and after that they come up with, this is the grip that we can produce, and that's what you see on screen.
Okay, thank you for your answer.
Unfortunately, we will not have wet tires. We will never run on the wet with this car, and we will never, it's not Le Mans 24 hours, so we don't need a tire that works at very low track temperature in the night. So we have a very specific demand for the 424.
Okay, thank you for your answer.
Yeah, no problem. There's a question on the chat. Could you describe your process how to transition the 424 vehicle model from on-shape to VPP? So obviously on-shape is where we do the 3D CAD design. Is the question related to the graphics only? So you're asking, how do you go from on-shape graphics to VPP graphics? Is that the question?
Yeah, I'm the one that asked the question. So yeah, like the graphics as well as like the collision between the objects.
Yeah.
Like how did you determine all that?
Yeah. So I'm lucky that I'm working with some great people to do that for me. So we have, and I like to, shout out to the people who have done this work. I'm in charge of the CAD design in Onshape, and I've done a lot of it, and some more people have designed the car with me. So we go from Onshape. This is where we design everything. And after that, we have Elio, who is a graphic design genius for real-time graphics for game engines like Unity. And it takes basically the model from Onshape and manually, it's a combination of imports using in Blender, I believe. And in Blender, is having to recreate texture maps and redesign some of the surfaces. So he's importing from Onshape and manually solving some issues with the geometry, because it's a completely different type of format, and then applying textures, and that's how we get the model that you've seen in VPP. As for the physics, they don't really come from Onshape. From Onshape, we get the mass of the objects, and then we build the bill of material, and that gives us the mass of the car. But all the physical models are more or less described in this Excel spreadsheet that I'm showing you. And they're different models, CFD, aero maps, tire model. There's also some models that I have described from my experience. And that's what I've done in the last 20 years, in this industry. And then I have Eddie, who is the mastermind behind VPP. And Eddie is coding everything in C#. Everything's in C#. So he's recreating all the models that I have created in Excel and rewriting everything in C# for Unity. So it's a lot of work, but it works well because we all have different ownership.
Thank you, Nico. I just have a quick follow-up question. Are these models, like for dynamic simulation, more simple And is this computationally expensive using Unity?
So what I found, I'm only a user of simulations. I have written a few simple simulations in the past myself, but when I met Eddie, I wanted to understand how efficient Unity was for physics. And I was really impressed. I had only worked with more professional grade simulators in the racing teams that I have been in. And I've been really impressed with the efficiency of Unity. We are running at 1 kilohertz, the physics. So 1 millisecond, every 1 millisecond, we have, all of these computed. The graphics is very fluid. And it runs on my laptop. Okay, it's a high-end, MacBook Pro, but it runs at 200 frames a second, which is amazing. So the way we look at performance, and I'm going to share Unity again. You see here at the top right, we've got frames per second. It's actually dropped to 140 frames per second. If I disable telemetry, it goes up to 230. Telemetry is quite intense. So 260, which is extremely fluid. If you have a lower end computer, it might go down to, you don't want it to drop below 60 because that's when you start seeing, steps in the graphics. So it's extremely efficient, I found. We are building, I should say, with Eddie, again, a completely new tire model that will be more complex with more contact points with the ground. Kinematically, it will be more accurate. There will be more joints and links in the suspension. And so far, it's looking like the performance is not going to drop much. So, I am impressed with Unity.
Thank you very much, Nico.
Okay, you're welcome.
Yeah,
Last
hi,
question
Nico.
I have. Sorry,
sorry.
Okay, go on.
Yeah. So you said you have you're using springs inside the wings, right? Under the wings, right? On the DRS wings. So my question is like, as you know, if a car goes over the bump or is there any altitude change, the spring will bounce, right? And that will change the dynamic wing angle, and that may hamper the aero balance, right? And the downforce levels.
So the answer to that is actually no. The reason is the flap itself. So when you go over bumps, it's like you're shaking the car, and things that the mass of each part matters at that point. The flap is in carbon, is extremely light. It only weighs 1.5 kilos. And it's controlled by a hinge, and it's controlled by this vertical rod with the spring. And what's pushing on it is a lot of aerodynamic loads. So when you go over bumps, if you are the flap, actually what controls you is there's no inertia about it. You're still very much controlled by the aerodynamic load, the hinge, and the force from the spring. I hope, do you see what I mean? And it only really moves when the aerodynamic load is changing with velocity.
Okay.
There will be a little bit of movement on bumps, yes, but it will be very small.
Okay. All right.
But yeah, thanks for your question. And the last one on the chat is the tire degradation also impacts the compound. So we're in a situation with 4-4 where we are just doing the 1 lap 5 minutes. These tires, the type of tires we're using, they are used to do much more mileage. So but what we've decided is we don't take into account tire degradation. We'll have nearly 1 new set per lap, not per lap, but we'll use 1 set of tires for 3 laps, for example, and at that point it's extremely consistent. So tire degradation is not going to really come into play. The one thing that will come into play is the tire, what we call tire warm-up. It's how quickly the tire gets up to maximum grip. Because we are starting 3 corners before the start-finish line, the car is cold, but we have tire warmers. So hopefully that will allow. We have to make sure the tire warmers are conditioning the tire right, so that as soon as we go, the tires are ready. So that's one thing. In fact, actually talking about this, and I'm digressing here, one of the problems that I need to solve still is the brakes. The brakes are going to be cold to start, and it takes them 2 or 3 big braking events to get up to temperature. So actually we might have, one of the issues we might have for turn 1 and turn 4 is the brakes might be a little bit cold. And it sounds easy, but it's not easy to warm up brakes when the car is static. So that's, these are things to consider for this specific lap record. Okay, I will move on now to the last section I wanted to cover. We've got 20 minutes left, so time is flying again, which is great. Go back to that window. Okay. So power balance, and then we'll have a bit of suspension quickly. Again, I already actually mentioned it a lot. And it's how much power we are sending to the front motor. So you see here, front motor and the transmission and the diff, and then you'll have the drive shafts. At the rear, you see the two motors connected together, transmission and the diff. So we have a single battery, and we can, with software, we can decide exactly how much we want, how much power to the front versus the rear. So we've worked a lot on what we call torque maps. And believe me, it's there's quite a lot of experience and knowledge and clever bits here, but that make the balance, again, the balance through the corner, braking, everything very, very solid and together. So I won't go through all the details, but in a nutshell, these are the parameters we are playing with. All these parameters you find in VPP, it's exactly the same set of parameters. So Eddie's taken this and rewrote everything in VPP. So what we're saying is we are giving what is the battery maximum power, 800 kilowatts in regen as well. This is the amount of torque in overrun. I explained that when we're off throttle, there is a small slowing down of the motors, like a handbrake effect. And this is when the balance comes in. You see these 3 numbers. We have a power balance in drive, full throttle, 33%, power balance in overrun, off throttle of brakes, and power balance in full regen, 70%, full brakes on. You see this curve here, the blue curve. When you go, the axis is -100, which is full brakes, and then you release the brakes. 0% is no brakes, no throttle. 100% is full throttle. So this is drive area, this is regen area. And what we do is we go from 70% regen, release the brakes, and then we go to 15% distribution. And as we apply the throttle, we go up to 33. Just by playing with these 3 numbers, I could change a number here. I could put 0% instead of 15. Everything will move up. You see that drop to 0. And all these curves are showing you the array of curves is is 10% of throttle steps and brake steps are showing you the amount of torque delivered by the motors, front and rear, the total for the car, and then the balance changing between the brake. Sorry, this is the total power. This is the balance plot. That's the braking, so it's not constant because there's also friction brakes coming into play here, so there are some variables. We also have limitation on power and torque for each motors. But you can see that full brakes, we are at the 70%. Release the brakes, you see the steps going down to 0, and then throttle on back up to 33. So all these plots are showing you exactly, it's like the mapping of how much power, where is it going, front and rear, purely based on throttle brake and the speed of the car as well. So it's only 3 parameters. throttle brake, and the velocity of the car. And from there, we describe exactly the software is going to use these maps and these parameters, and it will demand a certain amount of torque from the front and the rear motors. And all of this happens each millisecond on the real car. Every millisecond, we are recalculating this as well, or 2 milliseconds. And the torque delivery from the electric motors, which I absolutely love, is nearly instant. It's only 5 milliseconds to get what you want. So it's pretty amazing. So it's a bit like a video game. These cars really are software. You can drive them with the software, in that sense, or set them up with the software. Okay, so I wanted to show you these torque maps spreadsheets. Obviously, there's all the calculation in the background, but just know that this is exactly what's behind, in the computer of 424, this is what we're going to have. And that's what we have in VPP. We also have things like, well, because I'm showing this, the speed limiter is this parameter here. When we change the speed limiter for these sections, say I put 70% of the speed, you see how it's cut the power based on speeds? That's how our speed limiter works. When the motor speed reaches a certain amount, it cuts the power automatically. Okay, I can go in more details, but I won't go into much more today. And the last section, and then I'll take final questions. I haven't spoken about suspension yet, and I know, again, for a lot of people, vehicle dynamics is about suspension and dampers and things like that. You're gonna have to bear with me just a second. I need to plug my laptop because it's gonna run out of charge, so I'm gonna do that. Okay, we are back. Much better. So I haven't spoken about suspension yet, only because I wanted you today to understand that for this type of cars, it's very much, it's like F1. It's aerodynamics, power distribution, weight distribution before suspension. And that's why in F1, they only talk about aerodynamics or develop. You can see the suspension is compromised versus the aerodynamics because it's more powerful for this type of cars. But the suspension is still extremely important. But I'm only talking about how powerful these things are. If you work on cars that are slower speeds or less aerodynamics, like rally cars or GT cars, then suspension becomes a bigger factor in playing with car balance. Having said that, it is still extremely important. And because we talk about balance today, I'm just going to show you quickly some numbers here. This spreadsheet is a summary of, excuse me, is a summary for front and rear. There's various cars here. There's various references that I have used in the past. But take, for example, the 424. That green line is more or less how we're going to build the car. The one we use in VPP is the yellow line. The reason is at the moment there is no tire spring in VPP, and this is what Eddie is building, and we're going to have that very soon. So we have a slightly different setup on the VPP versus the suspension for the real car. That's the front of the 424. That's the rear of the 424. And for each suspension, we are defining the stiffnesses. We define the single wheel rate, so it's all in Newton per millimeter. So that will be effectively at the tire. So if you push with your hands vertically up on the tire at 100 kph, because it's speed dependent, because the suspension is not linear, It's not only one spring. Then you will get that stiffness, 220 Newton per millimeter. Now that's for a single wheel. For two wheels, so the axle, you push both at the same time, you will get 300. And then if you want to roll the axle, you will get a stiffness in Newton meters per degrees, 2,900. These numbers have been tuned, to mainly from a heave, which is vertical point of view. It comes back to aerodynamics a bit between the slow speed and high speed. You don't want the car to be too high in slow speed, and you don't want it to touch the ground in high speed. So you have a certain stiffness required, especially at the front. So you define these numbers for the front and the rear axle. You also have model parameters. So obviously what you know is that your tire has got a certain stiffness, vertical stiffness, which actually on this model is different to the one I've just talked about. So that needs updating. And then you have some springs. So you're changing the springs, the tire stiffness here, and you're looking at the resulting wheel rates and heave and roll rates. Once you've got the front and rear stiffnesses, then you can start looking at balances. So if you look at, so the roll stiffness distribution is how much stiffer is the front in roll versus the rear, or versus the total front plus rear. In this case, we're at 62%. In VPP at the moment, we are more like 54, but we are having a big update and these numbers are gonna keep changing a bit. But what I wanted you to see today is the front suspension on this type of cars, like 424, like same for F1, tends to be, is always stiffer at the front. Vertically, you see the single wheel rate, 74% stiffer at the front, or 74%. Yes, in this case, actually, I've divided front by rear, so it's not. Sorry, front to rear is here. Okay, 1.1. It's 10% stiffer at the front. The 62 is a balance. Sorry for the confusion here. It's the front divided by front plus rear. So we are 62% stiffer at the front, and all the balances I talked about today. Remember the weight was 47, aerodynamics was 45. They were more towards the rear. Now I'm saying the stiffness is more towards the front. And again, the reason is because by having a stiffer front suspension, you're allowing the rear to be a bit more free, and that will give you more grip. So again, you're actually favoring grip at the rear. And this is again for stability. This is because we have more load at the rear. We've got more power going through the rear wheels. So you can see it goes hand in hand with weight distribution, aerodynamic balance, and the general philosophy of the car. But at the track, we can change these numbers fairly easily. We change the anti-roll bar typically, and we can change this number this way. Look, if I take the 424 baseline, sorry, the no third spring here, we've got an anti-roll bar of 380 here, and at the track typically, I would change that to maybe a 200 if I want to soften the front slightly. You can see that my roll stiffness distribution has dropped to 60%. So that's a 2% step. At the track, we talk about these numbers as an engineer because we know 2% step will be felt by the driver. That step will allow the driver to have a bit more grip at the front. If he complains about understeer slow speed, you would do a step like that. Okay. I've gone back on this change. So this spreadsheet is calculating these balances of the suspension. So I will stop here, and I'll welcome any question to wrap up this session, please.
Yeah. Hi, Nico. I'm Shishak again. I'm sorry that I'm asking you so much questions.
No, that's fine. You're welcome.
Yes. So in the spreadsheet, have you considered roll resistance distribution? So let's say in a GT car, we have 80% roll resistance to 20%, like springs to anti-roll bars, right? 80% on springs, 20% on ARBs. Because let's say there is more load on ARBs, then sometimes ARBs fail, right? So there is a roll resistance distribution. So have you considered that?
Yes. So yeah, thanks for the question. So what you're saying is to do roll stiffness, you're right. We've got some side springs which are defined in this column, and the anti-roll bar will act. Both of them will act. And to define what we could have only one anti-roll bar only to do the roll stiffness,
Yeah.
or we could have only side springs.
Yeah.
But then the side springs also act in heave, vertical.
Yeah.
So you see, actually, we've got three options here. We've got one called baseline
Mhm.
that is using a side spring, a third spring, and an anti-roll bar.
Yeah.
Then you've got the no third spring option. So there's a 0 here, and you can see how because we don't have the third spring,
Yeah.
we have to stiffen up the side spring. And because the side spring's gone up, we want to keep the same roll stiffness, so we've gone to a smaller anti-roll bar.
Okay.
As a result, you get a very, very similar suspension.
Okay.
We've removed the spring, but we've changed the other two, and we get
Yeah.
pretty much the same heave and roll distribution. Then you can also have a suspension with no anti-roll bar.
The
It will
springs are
be
stiffer. Yeah.
yeah. So
Spring.
so your question is very valid. Is how do you decide what combination of springs do you want? Because there's more than one way to achieve the stiffness you want.
Yes.
And the answer is, so there's multiple answers. One can be, if the spring becomes too small, it will break. Like too small anti-roll bars can break because they still see the same amount of deflection. So you need a bigger diameter. So then you need to change your third and your side.
Yeah.
One of the big decision making for me is mass. So what I do is I compare the mass of the different options.
Okay.
And I want, and that's what Formula One does. Because Formula One, if you look at F1 cars, they have side springs, anti-roll bars, and third spring. You could say, well, they don't really need one of them. Maybe they don't need the anti-roll bar and they just do the other two. But when you do that, you find that the overall mass becomes actually higher because some of the linkage and some of the spring is become too big. So I found that distributing between three springs is the lighter way to achieve what you want.
Okay. All right.
It depends on the car you're working on.
But is there any distribution like percentage? Let's say you're running a third spring, so you have to set up your springs to be like 80% and then anti-roll bar to be 20%. And let's say you're removing the third spring, now you're stiffening your normal spring, side springs. Now they, let's say they are like 90% and let's say 10% on ARBs. So you're doing that.
Yeah,
The
and
distribution.
honestly, what we all I do is using spreadsheet like this, and
Okay.
that answers all your question because you have built in. You've got your three springs. You can change them independently and look at the results.
Okay.
So what
So
you need a tool like this so that you can answer these questions.
yeah, so like, so which combination is better, using all the three springs, right?
Okay, so actually I said that for me actually the best combination is that green for 4-4. It depends on
Yeah.
which car you work on. For 4-4, there will be no third spring at the front. There will be a side springs and an anti-roll bar at the front. But there will be a bump rubber on there will be a third damper on the bump rubber, but not a spring. It will only act at the very end. But at the rear, we are looking at a no anti-roll bar at the rear. The reason for that is purely packaging. The rear is very small packaging, and it's purely just we don't have the space necessarily to put an anti-roll bar. So it's easier. So you see the decision is made on packaging in this case. So it depends on the space you have and how your rocker mechanism works. It varies.
Okay.
It depends on your car.
Okay, so it basically depends on packaging, right?
Packaging, overall mass. Well,
Yeah.
the best thing to do is you need to evaluate 3 different options.
Mm-hmm.
If you have the time, you design 3 different suspensions, one with no third, one with no anti-roll bar, one with the 3. You look at it from a packaging point of view, and then from a mass point of view, and then you make a decision.
Okay. Okay, all right. Thank you so much.
Okay. Okay, great. So, Wes. Hi, Wes.
Oh, hello. I have a question. Does the effect of chassis stiffness affect the setting of the targets of the spring rates?
Yeah, so yeah, thanks for asking that. And I didn't talk about chassis stiffness yet. In the structure model, we will talk about module coming in 2 or 3 weeks. We will talk about it. Effectively, what links your front and rear suspension is a big spring, which is the chassis, right? And the chassis has got a torsional stiffness. And what we consider here is that in VPP, in our dynamic simulation, we don't consider it, because we consider that it's so stiff that it doesn't impact actually the vehicle dynamics. It's not true. In reality, there would be a small effect. But we are working with very big carbon fiber chassis. They have a very high torsional stiffness. So in our case, and the reason why you want this is that you want to make sure if you do a change of setup at the front, it only affects the front, not the rear. Imagine if you had a very, very soft chassis, then you could put whatever suspension you want at the front, a very stiff suspension at the front. The chassis would flex anyway. So your roll stiffness distribution would always be 50-50. You will not be able to stiffen up your front enough to make a difference. So yeah, you want your chassis to be stiff enough that that's not a problem. In the case of 424, it's an order of magnitude stiffer than the suspension, so it's not a problem.
Understood. Thank you.
Thank you. Okay, I've got one on the chat. So Yash is asking, how does the roll stiffness distribution front to rear affect understeer oversteer? So I think I've explained a bit, but I'll explain again. So if your roll stiffness distribution is to the front, which it is in our case, when you go in a corner, the load transfer or the reaction of the roll of the car is mainly done at the front. Imagine you've got a table with 4 legs, and the 2 front legs and the 2 back legs. And imagine the 2 back legs are on springs, and then you try and roll the table. There will hardly be any change in the vertical load taken by the back legs, because they will just deflect. But the front will be the one that will lift on one side and the other one will dig. It's the same for the car. You see the dig at the front suspension, you get that dig effect on the outside front tire and the lift on the inside front. So when you do that, then you rely more on one tire to produce your lateral force, and you start losing your overall axle potential has dropped. Instead of having 2 tires evenly loaded to produce your lateral load, you rely more just on one tire. And we've seen before that as you press more on one tire, you saturate it and your grip is dropping. So if you put all that together, the more roll stiffness distribution forwards or to the front, the more understeer, because you're losing front grip. So if I soften my front anti-roll bar, I will regain some grip at the front and lose a bit at the rear. So it will reduce the understeer level. Okay. Thanks for your question. I'll take a last question before we finish this. If there's any. No other question, no problem. And to finish, I'll put that image on screen. And just say, yeah, thank you for joining again. Really nice to see a good turn up again. And hopefully I see you next week for the next module. All right.
Thank you.
Thanks, everyone.
Thank you very much.
Thank you very
Bye.
much. Thank you, Nico.
Thank you, Nico.
See you next week.
Yeah.